lithium-ion technology, a technology that has become an integral part of our lives. Compact and powerful rechargeable batteries rely on it, as do energy storage systems. The digital revolution, electromobility, and even the transition to green energy would be unthinkable without it. But the technology has its disadvantages. Lithium-ion batteries still rely on rare earth metals and other natural resources. Many of the natural resources are being depleted, and some are even scarce. And the recycling of millions of batteries remains a challenge. Lithium-ion technology has played an especially important role in one sector, intralogistics. Intralogistics is the flow of goods and materials within a company. Although the industry relied on lead-acid batteries for decades, it is now swiftly transitioning to lithium-ion. E-mobility is revolutionizing warehouse operations and could pave the way for the technology in other industries. Hundreds of thousands of intralogistics vehicles are already equipped with lithium-ion technology. The first series-produced vehicles went online in the early 2010s. The intralogistics industry is booming, and so is the demand for lithium-ion batteries. The challenges that the automotive and other industries will soon face are already a reality for intralogistics. What lessons can we learn from intralogistics about developing the technology, sustainably sourcing the necessary resources, and above all, reducing their use? In warehouses all over the world, the future of e-mobility and the transition to clean energy are already happening. January 2020. An aging prototype of a staple of the logistics industry arrives without fanfare at Jungheinrich's corporate headquarters in Germany.
This is special because it's the first time lithium-ion technology has been researched and used in a concept forklift. A vision became a reality.
This futuristic-looking forklift was a quiet milestone in the world of e-mobility when it was unveiled in 2008. It was about the same time the first Tesla entered serial production.
When it comes to technological innovation, we always have to look 10 to 15 years into the future. In the early 2000s, we started to think about how we might use lithium-ion technology, which was still very new at the time, in forklifts.
Warehouse vehicles became pioneers in lithium-ion technology in intralogistics. But now the once innovative concept is embarking on its final journey. The prototype didn't make much of a splash. At the time, lithium-ion technology had one major drawback compared to conventional battery systems. It was very expensive.
We started developing the technology in 2007. We had a commission design a concept vehicle, a prototype. It wasn't intended for serial production. Only a technology freak would have bought that concept vehicle. It was unaffordable.
German electrochemist Jürgen Besenad played a key role during the early days of lithium-ion technology. Beginning in the 1970s, he and his team started researching lithium-ion technology at universities in Munich and Münster. Their work created the foundations for the rise of smartphones and electric vehicles, as well as a host of other devices so central to modern life. Researchers at the Helmholtz Institute in Ulm, Germany, are working on the next generation of electrochemical batteries. Lithium and solid-state batteries may soon join their lithium-ion colleagues. But researchers still face many challenges, including squeezing more out of the upstarts.
The biggest challenge we face is maintaining or even improving the performance of the energy storage material by replacing those materials with more sustainable alternatives. For example, cobalt. Cobalt enhances the overall function of the batteries, but finding a good replacement isn't easy.
The electrochemists work in protective gear in climate-controlled labs, testing and revisiting potential energy storage materials. They're hoping to find something that can withstand thousands of charging cycles and that is sustainable.
We analyze, test and retest to determine whether the material has what we need, and plenty of mistakes can happen.
Each cell they check costs time, money, and patience. And most cells aren't what they're looking for, but the project is still worthwhile.
You can see this cell won't work, unfortunately.
Research on batteries is proceeding at a fast and furious pace, propelled by the rise of e-mobility. The industry is closely watching the research. In this competitive industry, any promising material could be worth billions. But the lithium-ion battery is already facing stiff competition in e-mobility: hydrogen. Many experts are betting on hydrogen as the key to sustainable power for many uses. But it offers just few opportunities for Intralogistics.
The big challenge is where to get the hydrogen. Only a handful of customers today have access to their own hydrogen supply or filling station. Hydrogen filling stations are very, very expensive, as is transporting hydrogen. Hydrogen fuel cells do exist, including ones for forklifts, and they work. But complexity and cost are a major challenge.
Electric drive systems have been a fixture in the intralogistics sector for decades. Hydrogen will have a tough time gaining a foothold, in large part due to questions of costs and sustainability.
Producing hydrogen from electricity is energy intensive. Some of the electricity that goes into the production is lost from the outset. And converting the hydrogen in the fuel cell into electricity to operate a vehicle is also an energy intensive process. In the end, a hydrogen cell is far less efficient than if I take the electricity that's generated and store it in a lithium-ion battery.
A hydrogen-fueled forklift would consume 2 to 3 times more power than one fueled by a lithium-ion battery, so it's not viable yet.
We think this technology will continue to exist, but only a few customers will care.
A decade ago, only a few people realized that lithium-ion technology could replace the standard lead-acid rechargeable batteries used in forklifts. The first lithium-ion powered mass-market forklift was introduced in 2011, and it was made by Jungheinrich in Hamburg, Germany.
When it was launched in early 2011, the EGE 112i was the first forklift with lithium-ion technology in series production. It was a milestone in what was an emerging field.
Even though the EJE wasn't a major commercial success, it helped spur a revolution in the industry.
We're still learning from it, not what a battery looks like, but how it communicates, how to estimate service life, and how to test a battery before market entry. We're ahead of many competitors.
Although lithium-ion batteries were maintenance-free, had twice the storage capacity, and recharged up to 5 times faster than conventional rechargeables, the EJE was still too expensive to be competitive.
The lithium-ion battery was revolutionary mainly because it offered a dramatic improvement in storage capacity and output voltage.
Scientists continue to improve lithium-ion batteries as they pass their 10th birthday. They're still an industry mainstay, and some are convinced they could help propel the transition to green energy.
Lithium-ion batteries are still a flagship technology, and there's still a lot of potential for improvement. I think storage capacity could still be doubled, but we also have to consider sustainability and the fact that in 10 years, we might need 10 times as many batteries. Although the supply of lithium is large enough, there could still be shortages from supply and delivery bottlenecks.
Schnell genug bereitgestellt werden kann.
Lithium is currently mined in only a few regions of the world. In Chile, massive quantities of water are used to extract lithium from arid salt flats. In Australia, lithium is mined in open pits. Europe and Germany have played little role in lithium extraction, but that might soon change. A new project at the Karlsruhe Institute of Technology is turning heads in the industry. A team of scientists are researching a technology that might bring sustainable lithium mining to Germany. The key is water.
We've
been looking at how we can use the geothermal waters of the Upper Rhine Trench and have developed a technology in the lab for extracting lithium by filtering lithium carbonate out of the thermal water.
Thermalwasser des Oberrheingrabens herauszufällen.
In the competition over scarce resources, extracting lithium from thermal water could be a game changer for Europe and Germany. The valuable element can already be filtered out in the lab, but scaling it up for use in geothermal power plants is a challenge.
One of the big challenges is the high flow rates in these power plants. You see flow rates of about 30 to 80 liters per second, which is what makes lithium extraction viable. And you have high pressures of 20 to 30 bar and water temperatures of 60 degrees Celsius on average. Those are the main challenges.
Das sind die großen Herausforderungen.
A rare and highly sought-after resource, already in use by existing power plants. Obtaining lithium from water could revolutionize the sustainability of rechargeable batteries. If the principle works in practice, up to 160 milligrams of lithium carbonate could be extracted from a liter of thermal water.
That's
lithium carbonate precipitate. This white powder is what the industry uses to make lithium-ion batteries.
Some sites in Germany are very promising for lithium extraction, but researchers still don't know how much lithium might be recoverable from Europe's thermal waters. The North German basin and the Rhine Trench are both encouraging. Soaring demand and the prospect for finding valuable lithium closer to home is sparking innovative ideas and solutions, including in Bruchsal, a quiet town near Karlsruhe in southwestern Germany. During the aftermath of the energy crisis in the 1980s, utility EnBW drilled a borehole to tap into thermal water deep underground. But when fossil fuel prices remained low, the project was paused. But a geothermal plant has now sprung up atop the borehole, with plans to extract even more from the steam and water.
This borehole extends 2,540 meters underground, where there's a natural thermal water deposit. The water is 134 degrees Celsius, and we use its energy for district heating and electricity. And we hope it will supply us with lithium in the future. We've known for a while that the water is rich in lithium. We considered it in 2012, but at the time, lithium was less important. Then, lithium-ion batteries came along. In cell phones, in laptops, in electromobility. And suddenly, demand was huge.
Thermal water is spring water with a temperature of at least 20 degrees Celsius. The Bruchsal thermal power plant draws its water from a depth of more than 2.5 kilometers. The enormous pressure underground means the water is well over 100 degrees Celsius. Lithium wouldn't be filtered out until after it's been tapped for heat and electricity production, reducing it to about 60 degrees Celsius. The Karlsruhe Institute of Technology first filters the lithium ions out of the water and then precipitates them into a salt. High-quality lithium carbonate. The thermal water is then pumped back underground. It's a highly complex, evolving process with a promise of sustainability. "30 liters of thermal water per second, or 2.4 million liters per day, flow through the plant. If the plant extracted 70% of the lithium content, that would yield about 800 tons of lithium carbonate every year, enough for up to 20,000 car batteries. The battery for a very special prototype was produced here in 2017. It was the first Intralogistics vehicle equipped with a permanent lithium-ion battery. The prototype meant that one of the world's largest forklift manufacturers was switching to lithium-ion technology. The benefits finally outweighed the drawbacks.
The advantages of lithium-ion technology are obvious. For example, lithium-ion batteries have a very high energy density, which means that a lot of energy can be obtained from a comparatively small battery. The vehicles can also be smaller and more compact, which is a true advantage.
The next generation of vehicles became even more compact and efficient, and the long service life and high energy efficiency of lithium-ion batteries also boosted sustainability.
Lithium-ion batteries cut carbon emissions in electric vehicles by 20% over lead batteries, and compared to a combustion forklift, a diesel forklift, an electric motor with a lithium-ion battery cuts carbon emissions by 50%.
Hundreds of thousands of lithium-ion vehicles are already in use in warehouses around the world, and the industry is striving for sustainability. The batteries are screwed together rather than welded, and they don't contain critical raw materials such as cobalt. Reuse and recycling are integral to the production process. The large-scale adoption of lithium-ion batteries in intralogistics has put the focus on recycling. The industry wants to ensure that a sustainable technology remains sustainable beyond its original intended use. It's a concept called Second Life. One German company produces new batteries and also recycles them, JT Energy Systems. The company specializes in intralogistics batteries. And business is booming.
This is the new production plant. It will go online in the next 2 or 3 weeks to help cover demand. We're expanding production. We're switching from lead-acid batteries to lithium-ion batteries. We're seeing a substitution effect, more lithium-ion and less lead-acid. Intralogistics is also booming, so we're actually seeing 2 effects, the substitution effect and growth.
The advantages of lithium-ion technology over conventional lead-acid batteries are so apparent that customers are switching. The forklift fleets of many global players are already lithium-ion, and many competitors are also getting on board. Ramping up production is also lowering costs. But what about spent batteries? What will the industry do about reuse and recycling?
We generally get batteries back that were sold about 7, 8, 9, 10 years ago. The latest generation hasn't been around that long yet, so it's hard to say how long they'll last. It could be 10 or 15 years, or closer to 6 or 7 years. We're currently expanding our capacity for repair, recycling and diagnostics.
The latest generation of batteries are designed so they can be given a second or even a third life.
This battery is primarily assembled with screws, and it can be dismantled just by unscrewing it. It's easier to break down than something that's welded together. 16 cells are inside here, for instance. If our diagnostics show that one cell is no longer fully functional, we can replace that cell, swapping it out for a new or a recycled cell. That's how we breathe a second life into this product.
A massive energy storage facility is under construction just 50 meters away. It's primarily made from used lithium-ion batteries from Intralogistics. It's an ambitious project with a lot of promise.
This hall is about 30 by 35 meters and will become a huge battery storage facility, something on the order of 20 megawatt hours. The energy in the grid tends to fluctuate. When an especially large amount of electricity is drawn from the grid, this facility can offset it.
A stationary energy storage system is just one potential second life for used lithium-ion batteries from the intralogistics sector.
A battery storage facility is very sustainable. We can store used modules here and use them to stabilize the grid. That also allows us to postpone the recycling process. Any module that could be defective is analyzed before it's installed. Then it might stay here till it's outlived its lifespan, or it might be passed on to another customer who wants to use it. We have to thoroughly check the cells before we install them in a module and a cell testing station. We already have a module test station, so we can classify modules as category A, B, C, or D. Category Ds have to be evaluated again at the cell level. That test station will be built later this year.
The test center is under construction about 40 kilometers away in the city of Dresden. It will be the first device of its kind equipped with artificial intelligence. The station's designers hope the unit will solve a problem that has long hindered the efficient recycling of lithium-ion batteries.
Testing lithium-ion batteries quickly and safely wasn't possible until now. When used batteries were returned, we wouldn't know what condition they were in or what they could still be used for. This device can tell us that quickly and accurately. And it can learn how to deal with new types of batteries. This is the brain of the AI system, which is how it learns. Later, when it's really smart, you'll be able to link a small device to the cloud and do the same thing that the big machine does, out in the field. A service technician could have a small unit like this and check the battery's condition in just 90 seconds.
Equipped with artificial intelligence, the test station will eventually become a mobile application that can assess the condition of every cell inside a battery. That information will make it possible to determine the best use for spent batteries. It's also vital for a sustainable and efficient energy storage facility.
You have to imagine the second life like this. A big truck drives up with lots of different batteries. What do we do with them? How many are scrap? How many can be reused? That's the first problem. Currently, it's done by charging and discharging every battery to count how many electrons flow into them. That takes between 5 and 8 hours per battery. A truckload takes a long time. And it's not just one truck, but a whole bunch of trucks. So the advantage is the time it saves, and I don't need to know anything about the batteries. The truck drives up, the batteries pass through the test station, and we see what condition they're in.
Artificial intelligence is also opening a number of other doors. AI can not only help diagnose used batteries, it can also make battery manufacturing more efficient and sustainable. And the more AI learns about a battery, the more information it can provide on its lifespan. If the Dresden-based company succeeds with its AI-based test system, they'll be able to considerably improve both the safety and the sustainability of lithium-ion batteries. And that wouldn't just affect the intralogistics and automotive industries. While hydrogen technology has some advantages for trucks and other large vehicles, despite its low efficiency, lithium-ion technology remains the key for helping many other sectors operate more efficiently and sustainably. Electrification projects are already enabling the switch from diesel fuel to lithium-ion batteries. One of the world's first fully electric front-end loaders is being built here. It uses batteries from Intralogistics, not the car industry, and they're nickel and cobalt-free.
The 2200 is the most sold machine in our class. It's a 2-ton machine which you can easily transport on a trailer. That's the reason that the first approach is electrifying the 2-ton class.
Another example of the potential of lithium-ion technology. The construction vehicles are quieter, more efficient, and significantly more sustainable.
It was a lot of development in the hardware software, but at the end, it drives more smoothly than a diesel machinery.
Lithium-ion technology has numerous applications, including construction and agricultural machinery. And new scientific advances are also enabling the switch from internal combustion engines and lead-acid batteries to lithium-ion technology. The Royal Swedish Academy of Sciences in Stockholm recognized the advances in 2019. Lithium-ion batteries, according to the Academy, had laid the foundation of a fossil fuel-free society. John Goodenough, Akira Yoshino, and Stanley Whittingham were awarded the Nobel Prize in Chemistry for their lithium-ion work. Another, and perhaps more exotic way to extend the lifespan of batteries is being studied in the University of Halle in Germany, where researchers are trying to create a self-healing battery.
We're developing materials that can be applied to battery electrodes as a kind of coating or protective layer. Those coatings then introduce a self-healing mechanism into the existing battery electrode systems.
It might sound like science fiction, but Binder and his team are already conducting small-scale studies. Will they develop a battery that can heal itself? A challenge, especially for newer, high-performance batteries, which demand even more from the components.
During charging and discharging, the electrode materials inside the battery are constantly changing volume. In other words, they're expanding during charging and shrinking during discharging. That also means that these materials, which are solid materials, will eventually experience wear and tear as their volume expands and contracts like a balloon, and eventually they break.
The researchers apply a polymer coating to materials that are experiencing significant stress. The coating is designed to reduce or even prevent cracks and damage to the battery, which could significantly extend the battery's lifespan. But the research is highly complex. Finding the right chemical compound for each material requires a great deal of patience and finesse, but the result is worth the effort.
When you build self-healing mechanisms into a battery, you potentially extend its life. That reduces the footprint of the technology. The footprint depends on the raw materials. So by reducing the raw materials, you also reduce your carbon footprint, which is rather important nowadays.
Have the scientists already solved the challenges posed by e-mobility? Is the technology ready for the mass market?
We're still at a relatively early stage of development. We can see that materials like this work in principle, but it will take a few more years before it can be successfully used.
One material that might help bridge the gap is Zinnwaldite, which contains lithium and is named after the Zinnwald region of Germany's Erzgebirge Mountains. Zinnwaldite can be found underground in massive quantities in the German state of Saxony. Not long ago, researchers developed a new process for extracting the lithium.
What makes the Zinnwaldite process so special is that we've learned how to deal with the chemistry of Zinnwaldite. We know how to do something with the lithium, iron, aluminium, and fluoride. We can extract just the lithium. But, and this was key, we can extract the fluoride too, the mineral we know from toothpaste and Teflon pans. We converted a costly environmental toxin, fluoride, to a product. And we extracted the lithium using a remarkably straightforward process, by heating it and pressing CO2 onto it. It's that easy.
The new process could liberate Europe from imported lithium.
That's what's great about it. We use ordinary CO2, which is normally seen as a climate killer, and we have no waste. We don't have to add chemicals, and our process chips away at CO2. What we end up with is lithium carbonate. We use only CO2, there's no waste, and for me, that's a process with a future.
Das ist für mich ein zukunftsfähiges Verfahren.
We're facing a massive glut of spent and damaged lithium-ion batteries. Will we be able to recycle them and recover the valuable metals and other materials? Is truly efficient and sustainable battery recycling even possible? Spent lithium-ion batteries have traditionally been melted down in a furnace at 1,000 degrees Celsius. The critical and valuable resources they contained were lost. Experts now believe that mechanical recycling is the best option and could handle the rising flood of spent batteries. At the world's oldest mining university in Freiburg, researchers have been studying how to best recycle lithium-ion batteries for more than a decade.
We're somewhere halfway down the path of developing recycling technology. We don't know everything yet, but we're no longer clueless like 10 years ago. In theory, we can now mechanically recycle a lithium-ion battery, and there are companies that do that. Now we have to figure out the finer details.
The wide variety of battery types made by many different manufacturers is just one challenge. But researchers are still convinced that mechanical recycling, disassembling and shredding the battery, is the right approach. AI and augmented reality could play a major role. Sometimes the layers of material that need to be separated are thinner than a human hair, and there are other challenges, too.
The EU has set good sustainability targets, which is part of the discussion. They've said, okay, 65% of this mass needs to be recycled, which still leaves 35% that doesn't have to be directly recycled. But we still have to extract a set percentage of nickel, cobalt, copper and lithium, and that's a challenge. If I have to extract 90% of a metal in the battery, then I need to get inside the cell. And I need to lose no more than 10% of the metal in the process. I think mechanical processes together with other processes can achieve that. Not easily, but it can be done.
Science and industry are coming up with innovative solutions and making an important contribution to the sustainability of lithium-ion batteries. But many recycling plants today are already working at capacity, and production waste will also have to be recycled, which has only partially been factored into the equation. The recycling industry is growing and accelerating, but will they be able to handle the millions of spent batteries that will need sustainable recycling by 2030? Second life storage facilities could make a difference. The first battery modules are arriving today at the 20-megawatt stationary storage facility. And this is just the beginning.
About 13,000 battery modules will be installed here. About 2,000 are used, the rest new. The used modules are on their last life, so there aren't all that many yet. But that will change, and it will increase the sustainability of our facility.
The storage facility is modular, so it can be expanded. That will allow the facility to store more and more energy over time, and it will extend the lifespan of the batteries by years. The engineers are also working to ensure safety, an important job in a high-performance facility filled with used batteries.
We have an AI system that monitors the modules to ensure fire and electrical safety. It gives us a lot of data, which we can assess down to the cell. AI helps us monitor this huge facility down to the smallest of details.
Artificial intelligence helps make the facility safe and scalable. Several facilities like this one can be monitored by a small workforce. And AI is also key to the cell test stations.
We can now take the cells out of the used modules, analyze them at the test station, and assemble them into a new, good battery module.
Research into more efficient and sustainable power units is continuing. Industry is also on board and has designed new and more efficient concepts for moving goods inside warehouses. One of the most promising ideas in the field of lithium-ion battery power is AMRs, autonomous mobile robots.
Energy efficiency
is always an issue. The vehicles behind me are very small, so they need batteries with a high energy density. With these small batteries, we go 8 hours on a single charge. That's remarkable for a vehicle that can carry a full ton.
These robots are small and agile. Their low weight also reduces their power consumption. Is this the wave of the future?
It's conceivable that we could use lead acid or conventional technologies, but there would be many disadvantages. We'd have to fully discharge the batteries to avoid a memory effect. With lithium-ion batteries, we can use short breaks in the workflow to do a quick charge. That way the vehicle keeps running for more than 8 hours. It might even manage 2 full shifts before it needs a full overnight charge.
In Munich, researchers are already working on the next generation of AMRs, which will be even more advanced.
So I'm currently trying to connect to the robot so that I can test if it can drive with the new pallet backpack and if it can lift and drop down the pallets. So the hardest thing, I guess, is to put everything together, like make sure that all the parts of the system are working together and integrate it. Well, for today the goal is that the robot moves the pallet from one station to another, so we will just let it drive and observe if it works.
The AMR is scheduled to go into mass production soon. Intralogistics can benefit from e-mobility solutions more quickly than other sectors, in part because warehouses are enclosed.
The lithium-ion batteries are also a key factor because energy is the decisive factor. Traditional energy storage solutions are much bigger. With those, our project would never have gotten off the ground.
Lithium-ion technology has already transformed the way we live and work today. As an e-mobility pioneer, the intralogistics industry is already anticipating the challenges and opportunities the green energy transition will bring. Researchers are working to design innovative and sustainable solutions and collaborating with industry to develop the next generation of lithium-ion technology. Together, they share the same vital goal: creating a better and more sustainable future.